Welcome to Biogas Basics. My name is Jürgen Kube, and this is the first of a series of presentations about the engineering aspects of the biogas industry. I operated my first biogas plant in August 2000 and worked in anaerobic fermentation and the biogas industry ever since. I'm a process engineer by trade with a doctor in bioprocess engineering. I worked both for technology providers and plant operators in the AD industry. Unlike solar or wind, the biogas technology development has low barriers to entry. Anyone with access to subcontractors and some project management skills can build AD plants. But that simplicity is deceptive. Biogas plants are incredibly complex, spanning agriculture, biology, chemistry, thermodynamics, fluid dynamics, and many more engineering disciplines. Yet much of the industry is fragmented. Small companies, limited resources, and no common knowledge base. That's why I'm sharing my experience. To invite discussion, to be proven wrong occasionally, and to shed light on the biogas basics. Let's start by challenging what we know is true about the biogas process. Let's start with biogas myths. A biogas plant is not a cow. A cow makes milk and meat. A biogas plant makes biogas. Cows have no evolutionary advantage from making methane. In fact, cows have developed several evolutionary features to specifically inhibit methane formation. The digestion system of a cow starts with a maceration and dilution step in the mouth. Then the feedstock enters the rumen, where it is fermented at around pH 6. While the low pH cannot completely inhibit biogas formation, it reduces methane formation significantly. Volatile fatty acids, or VFA, are generated in the rumen and taken up via the rumen wall into the bloodstream of the cow. The rumen is a dialysis reactor. The VFA are transferred to the blood via diffusion and active transport mechanisms, and blood is the dialysate. Large solid agglomerates of undigested feedstock are separated and regurgitated for repeated maceration. The next step in the digestive system is the reticulum, which acts as a screening step that prevents larger particles to enter the downstream reactors. After the reticulum comes the true stomach, which acidifies the mixture further with hydrochloric acid and kills off most of the non-spore-forming ruminant bacteria. The stomach is followed by the smaller and larger intestines. In the smaller intestine, the pH goes back to neutral and hydrolysis reactions take place. The large intestine dewaters the digested feedstock. If we want to reconstruct the cow as a reactor cascade, the rumen is a membrane bioreactor, both with a diffusive and active transport over the membrane and a convective screening step at the outlet. The true stomach is an acidic CSTR, the small intestine is a plug flow reactor coupled to a dialysis step, and the large intestine is a plug flow reactor coupled to a convective dewatering membrane step similar to ultrafiltration. Most AED plants consist of two neutral or slightly alkaline CSTRs in series. Even biogas plants with a hydrolysis reactor miss the distinctive feature of the rumen, the selective removal of volatile fatty acids, which allows the acidification reaction to continue. So next time someone points to a biogas reactor and mentions a concrete cow, remember that cows have distinctive design features to minimize the biogas production, whereas most AD plants are engineered with the maximization of biogas production in mind. Oxygen is often added into the gas phase of a digester to oxidize H2S to elemental sulfur, or is added to a digester with the feedstock. Methanogens, syntrophic acetogens, and some fermentative bacteria are obligate anaerobes. They comprise ion-containing enzymes that catalyze redox reactions such as hydrogenases and alcohol oxidoreductases, but also electron carriers like ferredoxin that are oxygen sensitive. So, does O2 in the gas phase kill the biogas process? The answer is no. For O2 to be toxic, it needs to be in the form of dissolved oxygen. But in this form, the oxygen is also available for respiration reactions. Methanogens and syntrophic acetogens live in symbiosis, with hydrogen-producing acidogens. They form flocks or granules. Facultative anaerobic bacteria in the flock will consume all O2 and keep the bulk of the liquid dissolved as oxygen-free. For O2 to accumulate and become toxic, the microorganisms must consume almost all soluble substrate so that there is nothing left to oxidize. This is not the environment in a biogas reactor and not its purpose. We can also look at the formula for the gas-liquid mass transport. The flow of O2 from the gas to the liquid phase in mole per hour and cubic meter is the volumetric mass transport coefficient, or KLA, times the concentration difference between the equilibrium and the actual concentration of dissolved oxygen in the liquid phase. While the latter is zero in a biogas reactor, the former is also not very large, and the same can be said for the KLA value. The KLA value is the product of the liquid side mass transport coefficient KL and the volume-specific phase boundary surface A. The KLA value depends mainly on the volume dissipated energy in watt per cubic meter. It is very low for biogas plants, somewhere in the region of 1 day to the power of -1. Bioreactors that are designed for gas-liquid mass transfer, for example for E. coli fermentations, have KLA values of up to 1000 hours to the power of -1. In these reactors, the mass transport of O2 into the liquid phase is so high that O2 can actually accumulate. To achieve such high mass transport coefficient, the required volume dissipated power or mixing energy is more than 1000 watt per cubic meter. Compare this to a biogas reactor, where the volume dissipated power is in the region of 2 to 5 watt per cubic meter. Biogas reactors do not have the mass transport coefficient to dissolve O2 in the liquid phase. This is also the case when O2 is sparged into the liquid phase. Gas-liquid mass transport requires energy input. Without energy input, there is no O2 transport into the liquid phase. The oxygen bubbles will flow through the digester, but O2 will not be dissolved in the liquid phase. The inverse is also true. Gases that are produced in the liquid phase and must come out, like methane and CO2, will have to accumulate far above equilibrium concentrations before they will leave the liquid phase and form gas bubbles. But this is for a different presentation. Okay, this is a very common mistake, and it is also very costly. A biomethane potential test reveals what volume of biogas or methane can be produced per mass of feedstock. The test will also give information about the degradation kinetics, meaning how fast biogas is released, and if there are different substrate fractions in the feedstock, some degrading fast, others converting more slowly. The picture shows a batch test with a single fraction and a moderate degradation kinetics. The test is done as a batch. At T0, a reactor is filled with inoculum and feedstock and brought up to fermentation temperature, and then the gas production is plotted over time. After the start, no more feedstock is fed, and no effluent is removed from the reactor. The only outgoing stream is biogas. As the substrate in the reactor is converted to biogas over time, the substrate concentration S depletes. These tests typically run for 20 to 40 days. A very common mistake in the AD industry is to look at one of those tests, proclaiming that 95% of the substrate has been converted after 20 days, and then conclude that a continuously fed reactor should have a residence time of 20 days to reach the same conversion. They confuse the time after the start of the batch or reaction time with the hydraulic residence time of a continuous stirred tank reactor or CSTR. These times are not the same. In a batch reactor, all fluid elements stay in the reactor for the same time. In a CSTR, some fluid elements leave the reactor immediately after they have been fed, while others stay in the reactor for several average residence times. In a batch reactor, substrate concentration at the beginning of the batch is very high. This leads to high conversion rates and high biogas production rates. The biogas production rate then slows down over time as the substrate depletes. In a steady-state CSTR, the biogas production rate is constant and so is the substrate concentration. The correlation between conversion factor and hydraulic residence time for a steady-state CSTR looks like this. The curve is much flatter than that of a batch. A single-stage CSTR will require very long residence times to reach near full conversion. I have a presentation mini-series about microbial growth, where I go through the maths in detail, but for this presentation, it suffices to say that the batch reactor is modeled by an exponential decay function, whereas the steady-state continuous stirred tank reactor is modeled as a hyperbola, which approaches full conversion much slower than the exponential decay. So, do not use the gas production curve of a batch test to determine the hydraulic residence time of a continuous reactor. Instead, model the batch test to determine the kinetic parameters, and then use the kinetic parameters in a model for a CSTR to calculate the residence time for the targeted conversion. Often, a CSTR cascade is required to achieve reasonable conversion rates. My mini-series about the mass balance of a biogas plant describes this in more detail. Speaking of hydraulic residence time, the hydraulic residence time is often defined incorrectly in the biogas industry. The hydraulic residence time is the average time a fluid element spends the reactor before it exits. Two things are important here. First, it is the average time. In a CSTR, not all fluid elements will spend the same time in the reactor. Second, it is the average time a fluid element spends in the reactor before it exits, meaning that it relates to the outlet stream. In reaction modeling, the hydraulic residence time is the integral from 0 to infinity of the product of time and exit age function E of t. I discuss residence time distribution functions in more detail in my presentation, The Case Against Plug Flow Reactors in AD, if you want to know more. A typical reactor has 4 streams: feed, dilution, biogas, and effluent. The hydraulic residence time is the mass of digestate in the reactor divided by the effluent mass flow. The hydraulic residence time is not the reactor size divided by the inlet or feed stream, but divided by the effluent stream. In heavily diluted systems, such as wastewater fermentation, the biogas stream is very small compared to the inlet stream, and external dilution is not required. For this application, the inlet stream is equal to the outlet stream. But for most other purposes, this is not the case. The higher the dry matter content of the feedstock and the higher the biogas yields, the higher the biogas mass flow becomes, and the larger is the difference between the inlet and outlet flow. When the dry matter content of the feed increases, it can also become necessary to add dilution material to the digester to handle viscosity or total ammonia nitrogen. These dilution streams can reduce the hydraulic residence time significantly. The same is true for liquid feeding systems that do not use digester effluent for mixing and diluting fresh feedstock, but use external dilution flows, for example from a secondary digester or from the digestate separation. These systems can also reduce the hydraulic residence time considerably. In the mini-series about microbial growth and kinetics, I give a mathematical proof for a first-order reaction why residence time must be related to the effluent and not influent. Let's look at an example. A digester has a reaction mass of 3,000 tons. It is fed with 100 tons per day of feedstock with 35% total solids, which has a biogas yield of 200 cubic meters per ton fresh matter. The biogas has a density of 1.3 kilograms per cubic meter. 5% of the biogas mass comes from the water incorporated during the hydrolysis. This feedstock is fed into a digester that can handle 15% total solids in the reactor. We can calculate the mass balance. No dilution is required. The effluent has a TS of 13.9%. The biogas mass flow is 26 tons per day. The remainder is the effluent, 74 tons per day. The hydraulic residence time is 3,000 tons divided by 74 tons per day, or 40.5 days. If we would have used the input flow instead, the hydraulic residence time would be 30 days. But that calculation would be incorrect. Now, let's assume that the digester can only handle a digestate with 10% total solids. We do the mass balance again and calculate a necessary dilution stream of 58 tons per day. The effluent stream increases to 132 tons per day, and the residence time drops to 22.6 days. The residence time almost halves, but the input-related residence time is still the same, 30 days, and still wrong. Now we assume that the biogas yield of the feedstock is less than expected. Instead of 200, it is only 100 cubic meter per ton. The biogas mass flow is only 13 instead of 26 tons per day. Additionally, because of poorer gas yields, more dry matter is left in the digestate, which will require dilution. The dilution stream increases to 279 tons per day, and the residence time drops to 8.2 days. This is a good example of the importance of the effluent-related residence time. In all 3 cases, the input-related residence time is the same, 30 days. But depending on the digester and feedstock properties, the output-related residence time varies from 40 days, which is plain sailing from an operational standpoint, to 22 days, which is borderline stable, to 8 days, which will eventually lead to acidification. The misjudgment of the required dilution amounts and subsequent lower hydraulic residence time is often a case for a digester underperformance. The residence time can also be defined as the volume flow of effluent divided by the net reactor volume. So why do I use mass flows here? Balancing mass flows offers a more coherent balance. 1 cubic meter feedstock and 1 cubic meter of digestate do not necessarily add up to 2 cubic meter of a feedstock digestate mix. Whereas 1 ton of feedstock and 1 ton of digestate are always 2 tons of a feedstock digestate mix with a 50-50 mass percentage. In both cases, we will need to know the density of the reactor effluent, but if we balance in volume, we will need to know all the mixing rules for densities. Mass balances are simply easier to calculate than volume balances. The incorrect definition of the residence time is widespread in AD and even made it into laws and technical rules in some countries. It is so common that any statements of the residence time in scientific papers should be disregarded as untrustworthy. Recalculate the residence time from the original data if possible. So remember, always calculate residence times from the effluent mass flow, never from the feed flow alone. Now, while we are at it, total residence times are not a thing. Total residence times are sometimes calculated by adding up the residence times in a reactor cascade, or by adding up all digester volumes and dividing them by the feed stream, or by the feed stream minus the biogas mass stream. It doesn't really matter. This total residence time does not give any information about the expected performance of the biogas plant. The mixing system and the requirement for dilution has a massive impact on the overall conversion factor of the plant, as we have seen in the previous slide. Further, the performance of a single-stage CSTR differs enormously from the performance of a CSTR cascade. Shortcuts and dead zones matter as well. Let's compare 4 different digester configurations, each with the same total reactor volume. The first is a single-stage continuous stirred tank reactor, or CSTR. Feed goes in, biogas and effluent go out. The single-stage CSTR is very robust thanks to a high residence time but has a low substrate conversion efficiency. Remember the flat end of the hyperbola in the CSTR versus batch slide. Because of the high residence time as the primary digester, dilution is not necessary in this example. Next, we split the reactor volume into 2 identical digesters. 2 CSTRs with half the volume show a better conversion than a single-stage CSTR, however. Because the conversion in the primary digester is only partial, it will require dilution in this example. Dilution is provided by pumping digestate from the secondary digester into the primary digester. If the recirculation stream becomes very large, the 2 stages effectively become a single-stage CSTR. But if the recirculation stream is small compared to the feed stream, the dilution works to a small effect. This way of combining 2 digesters is not very effective, and this configuration should be avoided during the design stage of the AD plant. Recirculation from a secondary digester only makes sense if the primary digester has been designed too small. Nevertheless, this is another example of how AD plants with the same overall digester volume can have different conversion efficiencies. The next example is a 2-stage process with similar volume split as the previous example, but instead of diluting with digestate from the secondary digester, we separate the digestate first and use the fiber-free and dry matter depleted process water for dilution. This reduces the dilution water demand substantially and keeps the hydraulic residence time higher in the 2 reactor stages. This configuration is the normal design for a high solid fermentation and is more efficient than the previous example. The best configuration is shown in the last example. The primary digester is big enough to convert the bulk of the substrate to biogas and establish a stable biocyanose. The post-digesters are in series, and the more the better, emulating a plug flow reactor. These 4 examples all have the same total residence time, but vary widely in their conversion efficiency. So, total residence time, not a thing. Many textbooks use the organic loading rate, or ORL, as a design criterion for biogas plants. The idea is that over a certain loading, the fermenter biocyanose will be overloaded and the plant will experience lower conversion and will eventually acidify. A number that is often reported is an organic loading rate of 3.5 kilograms organic dry matter per cubic meter reactor and day. In the early days of the biogas industry in Germany, exceeding this criterion was required for an innovation bonus paid on top of the feeding tariff subsidy. Technically, a single counterexample would falsify the thesis that the organic loading rate constitutes an upper limit to the feed rate of a digester. There are hundreds of commercial AD plants around that operate at much higher organic loading rates than 3.5 kilograms per cubic meter and day, but the myth persists. Take the example from the hydraulic residence time slide. A 3,000 cubic meter digester fed with 100 tons of feedstock with 35% total solids. Let's assume a 95% loss on ignition. The hydraulic residence time is 40 days, enough to establish a stable fermenter biocyanose and to convert more than 80% of the substrate to biogas. The organic loading rate in this example is 100 tons per day times 35% times 95% divided by 3,000 tons. We can assume that the density of the digestate in the reactor is 1,000 kilograms per cubic meter. The organic loading rate is 11 kilograms per cubic meter and day, much higher than the purported upper limit, yet the digester would be very stable with this residence time. So, where did the organic loading rate come from? Like many design parameters, the organic loading rate originates in the aerobic technology. The classical aerobic reactor for wastewater treatment is the aerobic sludge contact process, which consists of a reaction step and a separation step, typically a clarifier. By recirculating the aerobic biomass back into the reactor, the organic freight to the reactor and biomass concentration in the reactor can be controlled individually. At some point, the incoming organic load is too much for the aerobic biomass to convert and the reactor overloads. However, in a CSTR without biomass retention, the ratio of biomass in the reactor to incoming substrate is always constant at constant residence times. The conversion ratio of substrate to biomass is the yield coefficient YXS, typically 5 to 15% in anaerobic digestion plants. Before we go deeper into this train of thought, it might be helpful to clarify what the organic loading rate is. The organic loading rate is the organic dry matter concentration in the feed divided by the input-related residence time. In our example, 35% TS times 95% loss on ignition divided by 30 days input-related residence time, or 11.08 kilograms per cubic meter in day. There are two ways to influence the organic loading rate. Vary the feed concentration at constant feed, or vary the input-related residence time at constant feedstock composition. If the organic loading rate were a design parameter, both variations would lead to the same result. Let's look at the example biogas reactor. The digester contains 3,000 tons of digestate. It is fed with 100 tons per day. The plant makes 26 tons per day biogas. The effluent is 74 tons per day. We choose the yield coefficient to 11.1%. With this value, the plant will make 2.6 tons per day biomass. The biomass concentration is 2.6 tons per day divided by 74 tons per day, or 3.5%. The digester contains 3.5% times 3,000 tons equals 105 tons of biomass. So, in our base case, 105 tons of microbial biomass convert 24.7 tons of substrate and 1.3 tons of water to make 26 tons of biogas. We can calculate a biomass loading rate, or BML. This is not a commonly used design parameter, but we use it to emphasize the point here. 1 ton of biomass must convert 234 kilograms of substrate per day. Now let's halve the organic loading rate by halving the feed concentration. The residence time stays roughly the same. Does the ratio of substrate consumed to biomass in the digester drop? The answer is no. It actually increases slightly. Let me walk you through it. The TS of the feedstock drops from 35% to 17.5%. All other parameters stay constant. We can balance the plant. The TS in the digester drops from 14% to 6%. The biogas production drops from 26 to 13 tons per day. The effluent stream increases to 87 tons per day. While the inlet-related residence time stays constant, the actual residence time drops slightly from 40.5 to 34.5 days because of the reduced biogas production. We can repeat the biomass calculations. The biomass concentration in the digester and its effluent is 1.5%. The digester contains 44.8 tons of biomass. The microorganisms in the digester must convert 12.4 tons of substrate. So, while the organic loading rate halves, the biomass loading rate increases from 234 to 276 kilograms per ton and day. The slight increase is because of the drop in hydraulic residence time. What happens if we keep the feedstock concentration stable but halve the feedstock mass flow? First, the inlet-related residence time doubles. We can balance the digester again. The biogas production is 13 tons per day. The effluent stream is 37 tons per day. The TS in the digester is 14% again. The output-related residence time doubles as well to 81 days. The biomass concentration in the digester is 3.5% again, and the digester contains 105 tons of biomass, like in the first example, with twice the organic loading rate. The same amount of biomass must now convert only 12.4 tons of substrate and 1.3 tons of water to make 13 tons of biogas and 0.7 tons of biomass. The biomass loading rate drops to 117 kilograms per ton and day. 1 ton of biomass in the digester must convert 117 kilograms of substrate per day. Let's compare the two reductions of the organic loading rate to the base scenario. The first variation of the organic loading rate at slightly reduced residence time led to a slight increase of the biomass load, but the second change of the organic loading rate at constant feedstock composition but increased residence time did lead to a significant drop of the biomass loading rate. This shows that the organic loading rate is not a design parameter. It is not possible to predict whether a digester is stable based on the organic loading rate. However, the hydraulic residence time alone is enough to predict if the digester is stable or not. Remember the previous slide about the conversion efficacy of the batch reactor versus the steady-state CSTR. The conversion efficiency of the CSTR depends on the product of residence time and reaction constant, K tau, which is called the first-order Damköhler number. The organic loading rate does not appear in the formula. So why does the organic loading rate occur in so many scientific papers and textbooks? The organic loading rate correlates loosely with the inverse of the hydraulic residence time. Theoretically, the organic loading rate can be increased by either feeding more of the same feedstock or increasing the organic dry matter concentration in the feedstock. The former is easy, but the latter will push a biogas plant to its mixing limits. At some point, viscosity dilution will be required, which reduces residence time as well, so increasing the organic loading rate will almost always reduce the hydraulic residence time. In the early days of the biogas industry, when the mixing technology was still inferior and trace element addition not common, many biogas operators observed an empirical correlation between organic loading rate and biological stability or conversion efficiency. This empirical correlation found its way into textbooks and even laws. Remember the previous slide about the definition of the hydraulic residence time. The hydraulic residence time is almost always calculated incorrectly. If it would have been calculated correctly, i.e., based on the effluent flow, the hydraulic residence time would have been the better parameter for an empirical correlation of digester stability. Organic loading rates have a niche application in anaerobic wastewater reactors. These reactors use some form of biomass retention and separate the solid residence time from the hydraulic residence time. In one of the first publications about the upflow anaerobic sludge blanket or UASB reactor, Professor Lettinger pushed the loading rate to more than 100 kg COD, around 70 kg organic dry matter per cubic meter a day, unaware of the fact that later textbooks would limit the organic loading rate to low single-digit numbers. For CSTRs, the organic loading rate should not be used. It is a meaningless parameter. Use the correctly calculated hydraulic residence time instead. Methanogens double every 14 days in a digester. This myth can be found in textbooks and research papers. It has two components we can easily falsify individually. First, there is the assumption that methanogens are slow-growing. Again, one counterexample will falsify this statement. Here are the reported minimal doubling times of methanogens as a function of temperature. Forget the names. Methanogens get renamed every couple of years. Focus on the data points instead. Methanococcus janashi, a hyperthermophilic hydrogenotrophic methanogen, doubles every 25 minutes in free growth. I've grown it myself during my doctorate time. There is a correlation between maximal growth rate or minimal doubling time and temperature for hydrogenotrophic methanogens, but even mesophilic methanogens can double in a couple hours. Acetoclastic methanogens, for example Methanosacina barkeri, are a bit slower, but even they can double in less than a day. Even the slow-growing specialist methanosata doubles in less than 100 hours, roughly 4 days. So where does this myth come from? It has to do with the second part, the growing in a digester part. In a steady state, continuous stirred tank reactor or CSTR, the doubling time of all microorganisms is coupled to the hydraulic residence time. If some microorganisms would be growing faster than others, the system would not be in a steady state as the concentration of the first group of microorganisms would grow compared to the second group. So all microorganisms grow with the same doubling time. The question is, with which doubling time? I'll do the maths in my mini-series about microbial growth. The correlation factor is the natural logarithm of 2, which is around 70%. So in a digester with 30 days hydraulic residence time, all microorganisms double every 21 days. In a digester with 10 days hydraulic residence time, the microorganisms double every 7 days. If they cannot keep up with this doubling time, they will be washed from the digester. All microorganisms of the biogas process grow with the same doubling time, from the fast-growing fermentative bacteria to the slow-growing acetoclastic methanogens and syntropic acidogens. They do this by depleting their environment of substrate. The growth rate depends on the available substrate concentration and the presence of inhibitors. In an uninhibited biogas reactor with high residence time, no volatile fatty acids or VFA can be found, because the respective acetogens and acetoclastic methanogens reduce their concentration so far to synchronize their doubling times to the residence time. The VFA are below the detection limit of the VFA analyzer. So why don't we operate biogas reactors with 2 days residence time if all microorganisms can grow so fast? Biogas reactors never truly reach a steady state. Even in well-mixed lab reactors, There are always small disturbances in the feed rate or local substrate concentrations to which faster-growing microorganisms will adapt faster than slow-growing microorganisms. The faster-growing microorganisms are the fermentative bacteria in the acidogenic phase. After a positive feed pulse, they would grow faster, while the slower-growing VFA-consuming microorganisms try to catch up. The VFA would accumulate to such an extent that they will start to inhibit the VFA consumers. The classical example is the inhibition of acetoclastic methanogens by propionic acid and the inhibition of syntropic propionic acid oxidizers by hydrogen. The second reason is that at low residence times, the microorganisms must allow high substrate concentrations in their environment to keep up with high growth rates. And substrate for one group of microorganisms is a reaction product for another group, for example hydrogen and VFA. High concentrations of products will trigger product inhibition. I have a whole mini-series about microbial growth if you want to know more. So, microorganisms of the biogas process can double astonishingly fast in free growth, but in a steady-state reactor their doubling time is linked to the hydraulic residence time. They double with ln of 2 times the residence time. If some species cannot keep up with the residence time in the digester, they will be flushed from the digester, the so-called washout effect. If they can be replaced by a faster-growing species, the fermenter biocyanose will survive. If not, the reactor will acidify and the biocyanose will change significantly. Another very common biogas myth is the CN ratio. The idea is that the molar or mass ratio of carbon to nitrogen should stay within a certain range to prevent nitrogen inhibition or limitation. Only the latter part is vaguely true. The CN ratio can be used to assess nitrogen limitation, but nitrogen limitation is very rare in commercial biogas plants and only occurs in wastewater fermentation or in monofermentation of nitrogen-poor feedstocks, for example whey permeate. Most other feedstocks contain enough nitrogen to provide nitrogen for the biomass build-up in the digester. Nitrogen limitation can be more accurately assessed with the nitrogen mineralization degree. There is a fixed ratio between biogas and microbial biomass produced. As a rule of thumb, the biomass production is around 5 to 10% of the biogas production in mass terms. Roughly 10% of the produced biomass is nitrogen. This is the minimal amount of nitrogen required for the biogas production, around 0.5 to 1% of the produced biogas mass. It does not depend on the carbon-nitrogen ratio, but on the biogas yield and nitrogen content. Excess nitrogen in the feedstock will be converted to total ammonia nitrogen, and its concentration will contribute to the nitrogen limitation kinetics. I have a presentation about the stoichiometry of the biogas process where I talk about the nitrogen mineralization degree in more detail. The impact of total ammonia nitrogen on the growth of microorganisms is covered in the mini-series about microbial growth, especially in the presentation about the growth of methanogens. Nitrogen inhibition cannot be addressed by the CN ratio. Adding more carbon to a digester does not overcome the nitrogen inhibition. Even if the carbon is converted to biogas and biomass, the yield coefficient of anaerobes is low and the amount of nitrogen bound by the carbon uptake is very small. As mentioned previously, somewhere in the region of 0.5 to 1% of the produced biogas mass. More importantly, the CN ratio does not distinguish between inert and biodegradable carbon. Straw, for example, does contain a lot of carbon and very little nitrogen, but only roughly half the carbon is biodegradable, while the other half is lignin or cellulose, protected by lignin layers. If the CN ratio were a parameter to assess the digester health, adding more straw to a nitrogen-inhibited digester would ease the inhibition. In reality, it would just block the digester. Microorganisms cannot sense carbon in the digester, especially if the carbon is in solid form. They live in the aqueous phase, and solid particles will form a separate phase which is inaccessible. When microorganisms degrade solids, they dissolve them from the surface. Microorganisms can sense solubilized carbon around the surface, but they cannot sense how big the particle is and how much carbon is in it. The impact of nitrogen on the growth of microorganisms can be described with a Haldane kinetic, which is a monokinetic extended by an inhibition term. The bioactive form of nitrogen is aqueous ammonia, in its uncharged form. The dissociation equilibrium of ammonium depends on temperature and pH. More of this in the mini-series about microbial growth. So where did the CN ratio come from? Like many process parameters, its origin lies in the aerobic technology. Aerobic microorganisms have a higher biomass yield than anaerobes. With respiration, microorganisms can convert up to 50% of the substrate mass into biomass. With fermentation, the ratio drops to 5 to 10%. The nitrogen demand for an aerobic cultivation is simply higher. Aerobes convert excess nitrogen into nitrate and nitrite, which are toxic byproducts. The aim of aerobic wastewater treatment is to create an effluent that contains neither dissolved carbon nor dissolved nitrogen. If the CN ratio is not within its bounds, it might be necessary to add an additional carbon source like ethanol, methanol, or glycerin to the denitrification step. In anaerobic technology, the CN ratio plays no role. Nitrogen limitation and inhibition is assessed by the concentration of free ammonia in the digestate, which depends on the total ammonia concentration, ammonia and ammonium, the pH and the temperature of the digestate. Nitrogen inhibition is overcome by adding more nitrogen-free water into the digester, not by adding more carbon. Speaking of nitrogen inhibition, a common biogas myth is that the separation of digestate and recirculation of the liquid phase will lead to an accumulation of total ammonia nitrogen in the digester. This myth has its origin in chemical reaction engineering. If a product stream of a reactor undergoes a selective separation step, and one of the streams leaving the separations is recirculated back into the reactor, inerts can accumulate in the loop. Therefore, a small bleed or purge stream is required to remove said inerts from the loop. All inerts will eventually leave in the purge stream if the separation is 100% selective. This effect is very small when it comes to total ammonia accumulation in a biogas plant. First of all, the separation step is not very selective towards total ammonia nitrogen. Total ammonia nitrogen is water-soluble. It will be distributed in solid and liquid digestate like the water flow. If 30% of the water ends up in the solid digestate, 30% of the total ammonia will end up there as well. All common separation apparatus, like a decanter centrifuge or a press screw separator, show the low selectivity. Second, not all the liquid phase from the separation is recirculated back to the digester. If the recirculation stream is in the same order of magnitude as the input stream, the dilution is already quite high, and the digester must become very large to provide enough residence time for the feedstock and the dilution material. Let's do a quick example. A 3,000 tons digester is fed with 100 tons per day feedstock with 35% total solids and a gas yield of 200 cubic meters per ton. The biogas density is 1.3 kilograms per cubic meter. 5% of the mass of biogas comes from water incorporated in the hydrolysis step. The feedstock contains 2% total nitrogen on a dry matter basis. The nitrogen mineralization degree is 40%. We have discussed this example before. The TS of the average digestate is 14%. The digestate is separated into a solid digestate with 25% total solids and a liquid digestate of 5% total solids. First, we calculate the amount of solid and liquid digestate produced by balancing the dilution and separation step as one control volume. The ingoing stream is the average digestate at 74 tons per day with 13.9% TS, and the outgoing streams have 5% and 25% TS. We can use the rule of levers to calculate the amount of solid and liquid digestate produced. The solid digestate stream is 74 tons per day times 13.9% minus 5% over 25% minus 5% or 33 tons per day. The liquid stream is 74 tons per day times 25% minus 13.9% over 25% minus 5% or 41 tons per day. The two streams add up to 74 tons per day. Now we assume that the digester can only handle up to 10% total solids. We have to recirculate some process water to dilute the digester effluent. The necessary dilution stream to reach 10% TS in the digester effluent is 74 tons per day times 13.9% minus 10% over 10% minus 5% or 58 tons per day. The effluent stream increases to 132 tons per day and has 10% total solids. Now we can balance the nitrogen stream. For this, we split the digester into a digestion and a dilution step. The outflow of the digestion step is the average digestate calculated before we added the dilution. The input stream of organic nitrogen is 2% of 35% of 100 tons per day or 0.7 tons per day. 40% of this stream will be converted to total ammonia nitrogen, 0.28 tons per day. The concentration in the average digestate is 0.28 tons per day divided by 74 tons per day, equal to 0.378% or 3.78 kilograms per ton. We know that total ammonia nitrogen is water-soluble. The water stream in the solid and liquid digestate is 24.8 and 39.0 tons per day respectively. 61% of the water and the same amount of total ammonia produced goes into the liquid digestate. The concentration in the liquid digestate is 4.18 kilograms per ton, which is also the concentration in the process water that is used to dilute the digester effluent. We can simply calculate the total ammonia-nitrogen content in the digester effluent by adding the average digestate to the dilution process water. The concentration is 3.96 kilograms per ton, which is only marginally higher than the concentration in the average digestate, 3.78 kilograms per ton. And this solution is for the steady state, so there is no further accumulation over time. My mini-series about the mass balance goes into more detail around the nitrogen balance. The nitrogen accumulation due to process water recirculation is marginal. In the worst-case scenario, when the recirculation stream goes to infinity and the residence time to zero, so not a very realistic scenario, the concentration in the digester effluent approaches the concentration in the liquid digestate, which corresponds to a 10% accumulation in this example. The reason for high total ammonia nitrogen in a digester is not the recirculation of liquid digestate, but the high concentration of total nitrogen in the feedstock. If the feedstock is diluted with external water, less internal recirculation is required. It looks like the total ammonia nitrogen accumulation stems from process water recirculation, but the dilution with external water simply dilutes the total nitrogen in the feedstock. So, process water recirculation does not lead to a significant total ammonia nitrogen accumulation. It is the high total nitrogen concentration in the feedstock that causes high total ammonia nitrogen concentrations in the digester effluent. If in doubt about nitrogen accumulation, simply make a quick mass balance covering the digester and separation step to quantify the accumulation. It will be marginal. The last biogas myth addressed in this presentation is the addition of buffer capacity to a digester that experiences acid accumulation to stabilize the biocyanose in the digester. The buffer capacity or alkalinity is the ability of the digestate to neutralize protons, typically in the form of bicarbonate and carbonate. It is measured in milligram calcium carbonate per liter. So bicarbonate would lose a proton and add a calcium ion to become calcium carbonate. The alkalinity is the sum of CO2 in its various forms in the liquid phase expressed as calcium carbonate. The myth is that the addition of bicarbonate or carbonate ions to digestate, for example in the form of sodium bicarbonate, would increase the buffer capacity of a biogas digester. This is not the case. Let's have a look at the fate of CO2 in the biogas reactor. CO2 is generated by microorganisms in its dissolved form as aqueous CO2 denoted by the AQ in brackets. The microorganisms also create an enzyme, the carbonic anhydrase, to speed up the conversion of dissolved CO2 to bicarbonate or HCO3-. Bicarbonate can react to carbonate. The dissociation reactions are generally equilibrium reactions helped by the anhydrase in the first step. The equilibria can be described with the pKa values. Aqueous CO2 is also in equilibrium with the gas phase. We ignore mass transport limitations here. This equilibrium is described with Henry's law. The Henry coefficient is the ratio of the equilibrium concentration of a dissolved gas divided by the partial pressure of the gas in the headspace. So, CO2 is produced in the dissolved form and reacts from there to gaseous CO2 or bicarbonate and then carbonate. Most of the CO2 leaves the digester with the gas phase, but some of it leaves the digester with the liquid phase. The ratio of CO2 leaving with the gas phase to CO2 leaving with the digestate depends on two main factors: the amount of water present, or the substrate concentration in the feedstock, and the presence of cations that can balance the negative charges of bicarbonate and carbonate. The thinner the feedstock and the more water is present to hold CO2 in its dissolved form, the lower the CO2 concentration of the produced biogas. Wastewater reactors often make a biogas with 80% or more CO2. Even if the feedstocks are carbohydrates that create a biogas with 50% methane and 50% CO2. This is because with more water present, more CO2 will leave the reactor as aqueous CO2. The concentration of aqueous CO2 depends only on the partial pressure of CO2 in the headspace. This concentration is always the same, regardless if the feedstock is highly concentrated like in energy crop fermentation, or highly diluted as in wastewater fermentation. If more water is present, more CO2 will leave as dissolved CO2. Further, wastewater reactors are often high reactors with a small footprint. This will increase the partial pressure of CO2 because of the hydrostatic pressure of the water column in the reactor. The second factor is the presence of cations. Digestate has a neutral charge balance. For every positive charge, a negative charge must be present as well. Positive charges are provided by strong cations like sodium, potassium, calcium, and magnesium. Strong anions like chloride, sulfate, and nitrate can partially balance them, though sulfate and nitrate will react to H2S and dinitrogen eventually. The third group of ions that can influence the charge balance are weak anion and cations, meaning their degree of dissociation will vary with the pH value. Weak cations are protons and ammonium. Weak anions are hydroxide ions, ions of phosphoric acid, H2PO4-, HPO4-2-, PO4-3-. Ions of volatile fatty acids like acetate, propionate, and butyrate, sulfide ions HS- and S2-, and finally bicarbonate and carbonate. Then there are also amphoteres like amino acids and surface charges of proteins that can act both as a base and acid. I will make a presentation about the water chemistry of the AD process in the future. There is a difference in the behavior of bicarbonate and carbonate compared to the other ions in the digestate. For example, the sum of ammonia and ammonium is constant. If the pH increases slightly, ammonium will be converted to ammonia, and the positive charge in the digestate will decrease slightly. This is also the case for all other species except for CO2. For CO2, it is not the sum of all inorganic carbon species, dissolved CO2, bicarbonate and carbonate, that is constant, but only the dissolved CO2. If the pH increases slightly, the dissociation equilibria will shift and more bicarbonate and carbonate will be formed. The amount of negatively charged ions increases. The reaction will never run out of CO2 because it is constantly produced, and the excess CO2 leaves with the gas phase. The sum of inorganic carbon species expressed as alkalinity is a result of exogenous input in the form of strong and weak an and cat ions present in the digestate. It is not a variable that can be influenced independently. The best way to increase the buffer capacity is the addition of caustic soda to the digester. The bicarbonate required to buffer the additional positive charge from the sodium ion will be provided by the CO2 formed in the biogas process. Adding more CO2 in the form of sodium carbonate or a bicarbonate or alkalinity-rich slurry to the digester will not change the buffer capacity. The added carbonate or bicarbonate will eventually leave the digester as CO2 in the gas phase. That concludes the presentation about biogas myths. I hope I could provide some new insights and challenge some old truths. Thank you very much for your attention, and I see you in the next presentation about biogas basics.